In this short presentation, I would like to address the importance of the Fast Fourier Transform. This is a fundamental tool for engineers, physicists, mathematicians. Over the last century, the increasing need for fast computations became a compelling necessity for scientific applications. To name a few, we have audio and image compression in MP3 and JPG formats, streaming video, satellite communications, the cellular network, and so on and so forth. As an example, consider the transmission, the storage and decoding of an audio signal. Many signals are highly compressible because most of the Fourier coefficients are small and can be discarded. And this enables much more efficient storage and transmission of the compressed signal, as only the non-zero Fourier coefficients must be transmitted. Therefore, it is necessary to rapidly encode and decode the compressed Fourier signal by computing the discrete transform and also its inverse. The Fast Fourier Transform algorithm, or simply FFT, embodies an enormous improvement over the naive discretization of the Fourier transform, which is called Discrete Fourier Transform, or simply DFT. Conceptually, the discretization of the Fourier transform is similar to the Fourier series. On this slide, you can see the mathematical formulation. It must be stressed that we have n squared operations to carry out with the DFT, because it returns a vector whose length is the same as that of the input data. Here, the input data contain n points, or samples if you want, and therefore we have n summations to carry out for each point of the DFT vector. N squared operations can be problematic, especially for a large data set, which is not unusual for scientific applications. Data sets can be large, of the order of billions of points. For example, audio is usually sampled at a frequency of 44 kilohertz. This means that a few hours of audio would lead to an order of a billion samples. Let's consider a data set which contains 10 million points, or if you want, samples. This means that the DFT needs to carry out 10 to the 14 operations. If we do these operations with a computer capable of performing a billion operations per second, we need 10 to the 5 seconds to complete the DFT algorithm, which translates to approximately 28 hours. That's way too much time. The Fast Fourier Transform, or simply FFT, is a brilliant way of drastically reducing the number of operations. This algorithm works well if we consider a number of samples which is exactly equal to a power of 2. However, it can be adjusted without great effort to be able to work with any number of samples. This is because we can always add some samples to our data set without causing any major interference with its spectrum. For example, by zero padding data, meaning adding zeros to our sample. Anyway, here for simplicity we assume that n is the power of 2, and it is 2 to the L to be precise. The algorithm works like this. It splits the number of samples into 2 summations. One summation is performed on the even samples, whereas the other is performed on the odd samples. We can rearrange some of the terms that we saw in the previous slides with some simple algebra. And this is where we arrive at. At this point, notice that the 2 summations have the same form as the initial summation. The only difference is that they are performed on a subset of samples which is half of the initial data set. Therefore, each of these 2 summations can in turn be split into two summations one more time, with each of them being a quarter of the size of the initial data set. The first summation can be split into two summations in this way. Similarly, the other can be split into two summations in this way. We have a tree structure that can be iterated. The first is divided into two, then these two branch off into four parts, and so on and so forth. The terms contained in the summation are halved each time, although of course the total number remains equal to n. The procedure is repeated for every integer k from 0 to n minus 1, and since the number of samples is n equal to 2 to the l, so it's a power of 2, the number of operations is of the order of n times l, which is n log base 2 of n. In summary, the FFT allows subdividing the data into small chunks at each level of the tree. We start from the bottom of the tree and then we move recursively back up. The number of operations at each level is small. That is why we can say that for each frequency we have an order of L operations. So in total, L times n, which is n log base 2n, since L is equal to log base 2n. To conclude, the Fourier transform can be discretized in two ways. The quote-unquote naive way is to use the IDFT algorithm, whereas the quote-unquote smart way is to use the FFT. The former requires an order of n squared operations to be performed. The latter requires n log n. For a large dataset made up of 10 to the 7 samples, considering 10 to the 9 operations per second, the DFT works out the computation in about 28 hours, whereas the FFT takes less than 1 second. This is probably the most suitable way to finish this short presentation, highlighting the marked difference between these two computations.